Welcome to another video in the series about the TI ARM Clang compiler. This is the second of two videos which explain common issues related to link time optimization. My name is George Mock and I'm your guide. In this video, the acronym LTO stands for Link Time Optimization. LTO is introduced in the video titled Link Time Optimization. I recommend you view that video before viewing this one. LTO is new to many, and therefore confusion and doubt about it is entirely normal. These two videos dispel all of that confusion and doubt, one issue at a time. Before getting into the issues, I want to explain some conventions about the code examples. You'll see the code examples in separate boxes like this one, like these two, and these separate boxes are intended to represent the fact that the code is coming from different files. So this is a convention that is applicable only within this video. Furthermore, the code examples are not typical of what you would write in your own code. Instead, each example is written to illustrate some particular point. Please focus on trying to understand that point and try your best to ignore how not typical the code is written. Please consider this example about how inlining may disable memory placement. In the first file, there's a function named uses many cycles, and it uses this function attribute to put it into a section, I run fast. The reason that is done is when the linker command file is written, there'll be an entry that puts I run fast into faster memory than several other functions are in. And an example of those several other functions is one in a different file. And the name of the function is calls many functions, and among the functions it calls is uses many cycles. Now, when LTO happens, you have to consider the possibility, well, what happens when uses many cycles gets inline inside of calls many functions? Well, when that happens, this key loop right here isn't in the I run fast memory, it's in whatever memory calls many functions happens to be in, which is almost certain to be slower memory. And so the whole optimization of putting this key loop in I run fast memory doesn't happen. The solution is to add another attribute to the function uses many cycles, and that attribute is called noInline. And it prevents the inlining from happening and preserves the fact that uses many cycles and the key loop it contains will be in the memory section I run fast. Please consider this example about how LTO may expose user error. In the first file, there's a line that defines a macro, HWReg for hardware register. And this is the typical kind of code that you see for reading from a hard-coded location. And there's a function named read that returns the value at that location. But assume that more happens than that. Reading this memory location will return different results with each read, or some sort of side effect in the system happens when it's read, or something like that, okay? In the other file, there's a function called doWork, and it calls read 3 times, copying the value returned to different variables and doing some work with those variables. Now, what happens in separate compilation, when these files are compiled separately, is that each call to read does occur. There are three reads of this location for the hardware register, and the side effects associated with those reads and all that, it all works just fine. And just to make this all a bit more interesting, presume that this code was written a long time ago by someone else who has since left the company, and so on like this. Now, let's assume that code like this is now built with LTO. You can tell by the tone of my voice that something goes wrong at that point. Well, what goes wrong? Well, what happens, or what can happen, is that the function read gets inlined into doWork, So it gets inline these 3 times. It's not a function call anymore. It's just, reading a memory location 3 times, okay? And the optimization part of the compiler will go, well, I read the memory location here. I don't need to read it there and there too. I mean, reading it once is good enough. There's no writes to this memory location, right? They only need to read it once, so it'll read it once, copy the value into V1, and then for V2 and V3, it'll just copy the value from V1 into V2 and from V1 into V3. And the net result is there's only one access to the hardware register when 3 is what is intended. This is the situation, okay? Which raises the question, well, what are you supposed to do about it? Well, the code should have been written this way from the beginning. There should be a volatile right here to indicate that there's some special properties associated with this memory location that the compiler cannot know about, okay? And when the volatile is present, that means every time the source code reads the hardware register, the compiler will issue code to do that read. Okay, that's what volatile is all about. And it's missing in this particular implementation that was written, in the case I talked about a minute ago, a long time ago, okay? So what's really happening here is that building with LTO is exposing an error that's been in the code for a very long time. This missing volatile should have been there from the beginning, but it simply isn't. And then it was hidden by the fact that it's, underneath this read in a separate file, okay? So this is a situation that's particularly uncomfortable, really, for everybody. I know, speaking just for myself, I really don't like being the person to tell an organization that, hey, the code that you wrote years and years and years ago has been working for you fine ever since. Well, it's always been broken. I mean, that is just not a pleasant message to have to convey. But if it's the truth of what's happening, well, then it is. And, I don't have much choice but to say, I'm sorry, you should have used volatile all along. And LTO can uncover this sort of thing, okay? And the solution in this specific case is to use volatile. And that's really the only way to move forward if you want to use LTO for code of this nature. This part of the video presumes you are a developer of a library, and it makes the point that you should always build that library with LTO. Presume you do build your library with LTO. In that case, your end customer remains able to make their own choice regarding LTO. If the customer uses LTO, they'll see improved optimization. If the customer does not use LTO, no harm done. The contrast is, suppose you build a library without LTO. Well, in that case, you limit the LTO upside for your customer. Okay? They'll still be able to build LTO on their own, and they'll get some lift from LTO, but it's limited because your library won't get to participate in the LTO optimization. In addition, there's a small effect on library build time from using LTO. This is the first of 2 examples that consider how LTO affects the overall amount of stack required by the program. So let's look at the code for this example. In one file, we have a function named level0. And under some unlikely condition, it calls another function called level1. And here's level1 in a separate file, and it uses an array of 100 bytes. So when these are compiled separately, level0 requires 0 bytes, and level1 requires 100 bytes. When you build with LTO, you have to consider the question, well, what happens when level1 is inline into level0? Well, in that case, level0 will now require 100 bytes, okay? But keep in mind, the overall amount of stack required by the entire program has not changed. It's simply sort of moved locations from level 1 into level 0. Now, what's with this unlikely condition? The reason I put that there is that I've run into cases where people can get a little bit deceived by this, because the way they're measuring stack usage, they're doing it somehow at runtime. One way to do it is you can fill stack with some unlikely value, and then you see, well, how many of those unlikely values were overwritten, right? And you can see how far into the stack does that take you. Well, if this unlikely condition does not occur, all right, and then level 1 is never called, you can be deceived into thinking that you need 100 bytes less than you really ought to reserve, right? Because even though the condition is unlikely, it's not impossible. And so because level 1 might be called, you need to reserve this 100 bytes right here when allocating memory for your stack. Okay? And so if you did that with a runtime check, and then you reserved an insufficient amount of stack, and then you go and build with LTO, all right, and then you're using this same technique to look at how much stack do I need, you can get surprised, right? So this is something to watch for when you're considering how much stack your program should use and you're building with LTO. And here's the second example of how LTO may affect stack usage. What's going on here? Well, we've got 3 files in this example. The first one has level 0, calling level 1 underscore A, and then level 1 underscore B. And I gave them those names because they're both at the same level, and then A and B, they're called independently. And then each of them has the same implementation. They've each got a buffer of 100 bytes. They're each using 100 bytes of stack. Okay. So again, you have to consider the question, well, under LTO and the possibility of inlining, what may happen, right? And it turns out it's a little bit complicated, but we'll get through this, okay? This table summarizes it, okay? If level 1A and level 1B are not inline, both of them are not inline, then the stack usage is 100 bytes. And this is the case when they're compiled separately, okay? You're going to use 100 bytes in this case because level 1A requires 100 bytes, then it's done. Level 1B runs, it requires 100 bytes, okay? Another way to think about it is they're never active at the same time. These two buffers are never active on the stack at the same time, and so 100 bytes for the both of them works just fine, okay? But let's consider the case where level 1A is not inlined, but level 1B is inlined. In that case, the stack usage is 200, because what happens? Well, level 1A is called, and its 100 bytes of stack happen, in its function. Level 1B is inline. Its 100 bytes worth of stack happens inside of level 0 now. So in effect, both of them are active at the same time, and so you've got to reserve space for both of them. Thus, they use 200 bytes. If the inlining is the opposite, A is inline, B is not inlined, same thing, okay? It's just which function is getting inlined. Now, the really interesting case is the fourth one, where they both get inlined. Now, your intuition probably tells you, well, you need 200 bytes in that case because you got both buffers, they're both active, and all this. And that, I understand why that's where your intuition leads you. Turns out your intuition is wrong, okay? It's 100 bytes. And why is that? It's because the compiler has its own optimization happening inside of the code, at the point in time when it's generating code for level 0. There's optimizations that understand that buffer A and buffer B are not in fact active at the same time, and so they can use the same memory even inside of level 0. So, like I said, this is a little bit complicated, but once you understand, how these buffers are or are not active at the same time, and that optimization happens when they're both in the same function, then this table starts to make sense. This is a good time to tell you that Code Composer Studio has a feature that helps you understand stack usage in your program. So when your CCS project is up, the way to see it is to go to View, Stack Usage, and you see it here. To make it bigger, take your mouse to this point, alternate click, right click, choose Toggle Maximized, and then here it is, and you can start to browse into it. This example contains an unusual situation, something that's not typical, but it gives you a sense of the effects LTO can have on a program. So this code is from the compiler runtime support library. It's the abort function. And the important thing to notice is that it has an ASM statement, and that ASM statement defines a label, that label right there. And the question to consider is, well, what happens if multiple calls to abort are inlined? Well, what happens is this ASM statement shows up in multiple spots, which causes a multiply defined symbol error, and it just goes downhill from there. You can't have that happening. So the solution in this case is to have the attribute no inline applied to the abort function so that inlining doesn't occur for it, so that you can guarantee a single instance of this label. Here is a caution regarding the function attributes retained and used. In this example, the attribute retain is applied to a function named never called. Okay? And presume this function is in fact never called in the program. Now by default, that is if the attribute retained were not present, by default LTO removes this function. However, the retain or used attributes override that behavior. So you want to apply those attributes only when you utterly and completely know they are necessary. You really need this function to remain in the program for some reason. Otherwise, memory gets wasted. I will end this video with two references. The first one is to ti.com/TIarmclang. This is the home page for the TI ARM Clang compiler. Here's where you can download it, access the documentation, and more details like that. The second reference is to e2e.ti.com. This is for customer questions on any TI product, including TI ARM Clang. If the question you post to e2e.ti.com is related to the compiler, it will be answered by me. Thank you for watching this video in the series about the TI ARM Clang compiler.